Good afternoon and welcome again to the SETI Institute's weekly colloquium series. And today we're going to go to Mars, courtesy of Dr. John Roma Skok, and we look forward to a very interesting talk. There's just a couple of things I wanted to announce before we get started with the formal proceedings. We have a couple of special people that we'd like to thank today for some very special help and support that they've provided to the Institute. So. First and foremost, what I'd like to do is I would like to recognize and introduce to all of you Leonard Tramiel. Leonard is an astronomer in his own right, a long time and good friend of the Institute, been supporting the Institute for many, many years. Also, for those of you who are regular attendees at the colloquium, you'll probably recognize Leonard as also a long-time attendee and big fan of the colloquium series. And Leonard gave a very generous gift to the Institute to help us support this colloquium series, a significant gift that really helps take care of the expenses of providing this and continuing to offer this wonderful colloquium free of charge to the general public every week, week in and week out, as we've done now for many, many years. And again, all of the video recording of the colloquium series available as YouTube videos. So anytime you like, you can go back and see the entire history of about 400 talks and growing. For the Institute's colloquium series. The index of the talks is available on our website, and it's really a rich part of our community outreach and service. So, Leonard, if you don't mind standing up just for a moment and take a bow, Leonard's gift is really making this possible. So Leonard is our first and primary sponsoring presenting sponsor for the colloquium series for 2016, and on behalf of the Institute, all of us at the Institute, the scientists of the Institute, our many guest speakers from all over the world, and of course for the audience that this supports, I want to thank you very much, Leonard, for your kind gift. So I'd also like to thank and recognize Dr. Jill Tarter. She was here a moment ago. Oh, there she is. She moved. Jill, as many of you may know, is one of the pioneers of SETI research, and Jill was kind enough to fund the design and production of the wonderful backdrops we have here up on the stage. After we left the colloquium site at the Institute, we needed new banners to provide backdrops for the presentations. You'll also see as you come in welcoming banners for the series and welcoming Microsoft employees to the series. We do have another event in January on the 12th, which will be opened up to the Microsoft employees. By opened up, I mean Microsoft will be encouraging their participation by providing lunch. So those of you, those of you who were here for the first one we did about a month ago, we filled the auditorium, and Microsoft was kind enough to feed their employees and our guests. It was a great event. The next one of those will be on January 12th. So we're becoming integrated into the Microsoft community as part of their Tech Talk series. So every month we hope to open it up in a big way. Microsoft employees are always welcome to attend, but when food is served, they tend to come in bigger numbers. And I fully understand that. So in any event, so thanks very much to Jill for her kind support and giving us the graphics and artwork. And without further ado, we want to go to Mars, so I'm going to turn the microphone over to one of my colleagues at the SETI Institute, Matt Tiscarino, and he will introduce our speaker today. Matt?
Our speaker today is J.R. Skok. J.R. was an undergraduate at Cornell University, where he worked with Jim Bell on Mars rovers. And then he was a graduate student at Brown University, where he continued to work on Mars with the near-infrared mapping spectrometer called XRISM that is on board the Mars Reconnaissance Orbiter. And while he was at Brown, he was involved in the discovery of volcanic hydrothermal deposits that are very possibly due to hot springs, ancient hot springs that were active on Mars 3 billion years ago. And since leaving Brown and receiving his PhD there, he has continued to work on this project and is in particular been looking various places on the Earth for analogs that we can study up close and understand how these hot spring activities on Mars might have functioned. And that's what he's here to talk to us about today. So let's welcome J.R. Skok.
Thank you all for coming out. Can you all hear me? Good? Okay. Yeah, so I'd like to share a bit about a project I've been working on that's going to be looking to pinpoint the search for life on Mars. There have been a lot of missions recently with Curiosity, seen there, and then the upcoming Mars 2020 where Habitability they've been looking for, and that's really got me thinking about how do we actually know where to look for that. And some of this talk is kind of my strategy to put together a mission to go and pinpoint life, and maybe it doesn't really fit a mission like that, but how do we develop a mission from those goals and develop it out? And so that's what I'm hoping to talk about today. A brief outline of what we'll be seeing. I want to go through a little bit of a history of Mars exploration, how we've kind of selected where we've landed and what does it mean and how that's kind of changed as our understanding of the planet has developed, and how that might mean for the next steps. How do we use the information we've gotten to kind of focus in on answering the questions that we have about the major differences and the major scientific findings and major desires for what we want to know about the planet. Then kind of selecting where I want to go. If I have these questions, where on Mars do I think we can best answer them? And then how do we want to develop a mission from that science out to get us there and answer what we want to see? I do want to point out that a lot of this project, especially towards the end, is very much a work in progress. This is right now the first year of a 3-year NASA grant where I'm going and developing a lot of these issues. And I'm a SETI researcher. I've been affiliated for about a year, but I'm still fairly new and haven't really talked to many of you. And so a lot of this is just me kind of telling you what I'm working on, and hopefully you've been doing similar work your whole careers and have some ideas about what steps I should take next, ideas for instruments, ideas for all the things I'm learning the hard way that maybe you've already done the legwork and would be willing to share for me. So please, hopefully this will develop a conversation. I'm at the SETI Institute almost every day. Find me, grab me, and please, hopefully this will get some chats going. So I'm going to start off with how we've come to know Mars. For most of humanity, this is how we've known Mars. It's been a point of light in the sky. It's something that we know is different than stars. We see it wandering around. It was one of the planets, the Wanderers. We knew it was kind of red, and that became the bloody sign of, put our gods there, Mars in some cultures, the god of war, and we kind of personified that in a way. And for most of human history, that's really all we knew. With the development of telescope ages, we could get a bit better view, and Mars started going from being a point in the sky to an actual planet. And so for several hundred years, this is kind of what we started to see of Mars. This is the first drawing I've ever seen, first data set, you can almost say, observations of Mars, where it's no longer a point in the sky, but an actual planet with places. Again, very kind of dark, maybe a sea at one time they thought it to be, but there's features of light and dark. Kind of showing what we may have gotten that. This is kind of an early telescope photo, and you can definitely see the kind of dark features that were recorded early on. And again, this is starting to become a planet, another world with polar caps, something that we can relate to. And in this way, from being a place for our gods to be an actual world that we can almost see like Earth, it really has changed how humans have perceived Mars. And this continued to kind of evolve with more observations to the kind of idea of the canals on Mars as an early thing where seeing some linear features and kind of extrapolating what we see on Earth to what could have been on Mars. And that created a very popular identity that Mars may have had life and civilizations even living on the surface. And I don't want to, it can be the fact and fiction of it can be kind of intertwined to this point, but it definitely has a strong, I think, link on the public which supports the exploration of Mars is the story of life on Mars. Even so much whether or not they're intelligent civilizations building canals to save their cities or attacking us. The life on Mars has been a powerful narrative for influencing public and even scientists to go explore. This continued that kind of up until the space age, where we were able to actually go there with a spacecraft. The first spacecraft to go to Mars, Mariner 4, really changed how we saw of Mars. The first spacecraft images were a little blurry, and eventually, even with the mission flying by, we were able to get a bit more and kind of saw a cratered world. All the ideas of cities and oceans and things that Mars may have been more like Earth kind of vanished with this mission. We saw a cratered world, something that looked more like the moon than like Earth. But it didn't really destroy our thoughts of life. Maybe it's just deeper. If we keep going deeper, we can find these evidence of life. And so that kind of changed how we'd want to view Mars, but didn't really stop our desire to go and search for life, search for what's going on this neighboring planet. I love this image. This is from a National Geographic, an old one in 1967. So this is after we knew that Mars was a desert, crater-filled world. Carl Sagan wrote in National Geographic, put this hypothesis of what life on Mars could be like. Maybe Mars is a desert world, like maybe the American Southwest. We have deserts and bushes and ground cover, maybe even a jackrabbit running by. From the early Mariner images, it didn't rule out this world. And so as late as 1967, fairly prominent scientists still could kind of have this view of what life could be like. And so continue on in the 1970s, we sent the Viking missions, both orbiters to kind of map the planet as well as landers to kind of go in and really search for what the life on the surface could have been like. This also starts to lead into kind of the interplay between the engineering and how we land. Early on these missions, these kind of show the kind of maps that we had to work with and the landing ellipses that we're trying to stick in this frame. And here we're trying to land on another planet with knowing very little. Just really the maps from early Mariner images. You see a few places where we have a bit more imaging data, and then the orbiters themselves, Viking orbiters, started taking data, and we were trying to put landing ellipses just to get on the surface without really knowing the issues. Nowadays, we talk about topography, atmospheric modeling. Here, they really didn't have any of that. And the idea was just to get on the surface, find some place flat enough to land, and they did. They landed 2 places and were able to survive and get their jobs done. And they found the rocky world, the Mars that we know today. It doesn't look like the desert Southwest, a bit more like the deserts of Antarctica. No real macro life living. We sent a life detector to actually go and search in the soils. They're able to take it, give them nutrients, and see if any kind of life would come and develop. And really nothing showed. And this was kind of the big dent that we realized that if life ever existed on Mars, it's not going to be easy to find. You can't just drop down on the planet and expect it to pop out. And this, I think, really kind of hit some of the psychological aspects too. Like going to Mars to find life, a big part of understanding that was a search for life, both in the public and in the scientific world. And that this kind of mission, these raw results really kind of hurt that process. And for a number of reasons, we just kind of gave up going to Mars. This shows the Viking missions in 1975, and for 15 years, we didn't really launch anything to Mars. And it was 20 years before the mid-90s when we started actually getting to the surface again, and now leading to the current armada of spacecraft on Mars today. And so next I'll be talking about kind of what's going on here and how our current Mars program has kind of worked into itself. So this here shows kind of our most recent Mars program from the mid-1990s, where we had Pathfinder, Mars Global Surveyor, a whole number of missions up into the future, InSight, and Mars 2020, as well as the kind of evolution of what we're looking for. If we go to Mars looking for life, that's a very dangerous thing. We're most likely going to, not be able to find it because it's a hard thing to do. And so when we go to Viking and we say we're going to look for life and we don't find it, that's going to hurt the program for a while. So we know we can find water, essentially. Like we've seen it so many times now, like finding water on Mars is now a joke in the community that it happens almost every other week. But that was kind of like just mapping it out, showing all the places, building up this data set of what these landform looks like was the point of these missions. And now that we know it's there, now the idea is to get a bit more refined, to go beyond that, to figure out what is the habitable environments. And that's kind of the age of MSL, the Curiosity rover, and Mars 2020 to kind of build on that. And I want to point out, especially when we're trying to develop these landing sites, these missions here, these are the orbiters. And they've really just completely changed our understanding of Mars, its surface, its environments. And the key here is the timing, right? So when Mars Pathfinder flew, which I'll talk about in a moment, we didn't really had, all the only information we really had of Mars was from the Viking era. The early large-scale images, some spectral data, but really mostly just like basic images. With Mars Global Surveyor here, we started to have high-resolution images. We had compositional data, and just a lot more data sets so we can try and figure out where our mission should go and what are the targets that we're looking for. And with each one of these missions, we really built up that database and were able to get better information of where we should go and how to find the targets we're looking for. And the kind of the timing here is critical too. So when MER flew, which I'll get to a bit more, we had data from here. And now when MSL flew, we had all these instruments to work with. And each time we send a orbiter there, it really has transformed our view of Mars, transformed what we thought good landing sites would be. And that kind of process, I think, is key looking forward. So getting back to Mars Pathfinder, this was after an absence for 20 years. The big goal here was just to get to Mars. And again, we didn't really have that much more information than what we had for Viking. And so we ended up picking a landing site here pretty close to where Viking was. It was a place that we already kind of knew from landing Viking. It was a place that was pretty safe. You can see very flat terrains. And the scientific motive was that maybe these channels could bring a diverse rocks from this whole outflow channel and put them there. So wherever we land, we might see some geologic diversity. And it got to Mars, it got us some experience roving. It was a very good success, but it wasn't a very targeted mission for science. It was mostly just proving that we can get back to Mars and getting that technology going. The next set, the Mars Exploration Rover, these are the first time that we're able to take these new data sets and transform them into a landing site selection process. Using the Mars Global Surveyor, especially Opportunity here, we actually flew to a compositional zone. This is an area that it doesn't look like it's very interesting. It doesn't look like it has water from just images. But based on the composition, we saw lots of hematite, a mineral often formed in wet areas. And so this was a place where we're able to use all that data sets we've been collecting to then select where we're going. Spirit, similarly, is we use topography, we use kind of context to look at a morphological site. We wanted to look for possibly a crater lake. This large channel, Medine Vallis, flew into Gusev. So the idea is if we land there, we might find the ancient lake. That story, if you've been following, is much more complicated than that, and that's for many other talks to talk about. But I just wanted to show how we've used these data sets to kind of target in, and how that's only gotten better. And so those are the Mars Exploration Rovers. And now I'm going to kind of group up the Mars Curiosity Rover and the Mars 2020. They're both very similar rovers, and how the kind of idea has created them. And so again, I'm in the community, but I'm outside these programs. So this is kind of my kind of very abstract view of kind of the process that happens. With both of these missions, it seems like there's an abstract growth. NASA kind of dictates what this mission is going to be about. With Curiosity, we wanted to expand on the successes of the Mars Exploration Rovers. We wanted to have actual laboratory-grade instruments on Mars, the most accurate instruments we've ever had on Mars, and be able to have enough mobility to take advantage of that. So that required that we had to have a big rover, enough to carry this, and it really constrained what the instruments could be in order to do that. For Mars 2020, the main goal was we wanted a rover to be the first part of a sample return. So it had to have a lot of mobility to go get samples, and it needed enough space to characterize them. And they wanted to really reuse the engineering from from Curiosity. And so that kept a lot of the legacy there and also put in some constraints. So they created those dictates. That created a rover design to kind of meet those goals. And we'll see, as I mentioned, how the design there then forces your payload and forces your landing constraints into certain bins, which then the scientific community needs to fulfill with proposals and lots of debate that is still going on for Mars 2020 for the landing sites. Then they call for instrumentation and landing sites, and that whole science teams try to fit what they want to do into the boxes forced by the engineering. And then, there's a name tag. It stuck to the floor, so that's going to stay there. And so once that happens, there are teams at NASA then selects these things. We pick the instruments. For Mars 2020, all the instruments have already been selected. They're being built, they're being produced to fit into the places the rover allows, and we're still debating this landing site. So this has some positives and some negatives. The good thing is that all these orbital data sets are still taking some data. They're getting a little old now, but they're still producing. And every day that we wait deciding where we want to land, what we want to do there on Mars specifically, gives us more time for data to come in, for scientists to look at it and figure out what is the best place to go. But the downside is that none of the rover decision itself, how we build it, what it can handle, is going to really throw away some of the landing sites we could go to. And by picking the instruments first, allows some lead time for them to be developed as long as possible before we can force where we want to go. But it also means that the instruments we select may not be well suited for the site we want to go. The instruments we might want to take to a delta or lake valleys to look at layers may be different than if we want to go to a volcanic site. And we kind of lose the ability to kind of tailor that with this kind of process. So that's the kind of pluses and minuses of this. And this kind of illustrates with the Curiosity landing site selection. These were the 4 kind of finalists for Curiosity. And you can see all these colors are basically the footprints of the images we had, mostly from the Mars Reconnaissance Orbiter. Incredibly high resolution imaging, mapped them all. We had compositional mapping, incredible amount of information. And with each of these missions, from Viking, where we had just the Viking orbiters, to Pathfinder, we had a few more. MER, we had all the Mars Global Surveyor. And now MSL, we had an incredible amount of data sets kind of went into this, allowed us to pick. So again, we have this kind of exponential rise, which favors building the craft first and then figuring out where to go. Because again, every day these kind of operate, you have a better idea where to go. And so this is kind of a timeline that NASA, the Mars kind of program puts out, kind of what we've been doing. We are about here. These missions have all flown. This is going to come, and then Mars 2020 is going to be going. And what we notice here is a lack of future orbiters. And I think this is really going to change how future Mars missions are happening. We no longer really need that lead time because most of the instruments that we have, most of the orbital data that we're going to have has already been collected. And we can look at it and reanalyze and reconsider it forever, but at the same time, it doesn't look like we're going to have any more transformative orbital data sets coming for a while. And so at some point, we just say, okay, these are the sites that we now say we must go to Mars. Maybe they might have been too hard for too rocky for this rover to get to, or too hard for their landing site to make. But maybe we can decide to go there and then build a mission that actually can survive it. So just to kind of illustrate that point, this is a map of Mars, and this was the Curiosity kind of early on in the Curiosity landing site selection. Because they decided that it was certain issues that can't handle the cold, they kind of laid out these polar areas. So the rover cannot go to the poles. Because of the landing site or landing methodology, in order to have that large of a rover land, we couldn't go high elevation. So these black areas were just gone. So all the places that Curiosity could go had to be in these kind of colorful areas near the equators. And these are all places that people have suggested to go. So you see a lot of the places that people wanted to go, the rover just couldn't do. So they were just thrown out immediately, despite being incredibly interesting science sites for each of them. And so Curiosity still had a crazy number of really great places to go, and it picked a really interesting spot at Gale. But again, by building this rover first, you really kind of eliminate some of the things you can do. So this is the end result, Gale Crater, where we finally landed. And it's an amazing result, right? The fact that we were able to land in the middle of this crater trawl between a large central peak and the rim is just an amazing work of engineering to kind of sit down in there. We're able to go to a place where we had geomorphology of water. We had some really great mineralogy. It's a very interesting site. And I really want to focus here on the kind of engineering that allows that, right? This is the landing ellipse that Viking had, right? That was basically to get someplace flat as we can do, it can win. Whereas by developing these systems, we were able to start to pinpoint almost, say this is more interesting, we want to go there. No other mission could really have landed here before this. And they keep on getting smaller and smaller landing sites, allowing us to get to more and more interesting geology, which is often in this kind of rougher terrain. And some of this, I think, leads to kind of a general tension we often have in these missions between this engineering and the science side. While all missions need to have teamwork between both. If a mission doesn't work, if the engineering isn't there, there's no science at all. But at the same time, we need to have a scientifically valid reason, a scientific worthwhile reason to go there. And so there's always this kind of tension. Engineers, they want the safe landing site, and where scientists really want the exciting. They want someplace new, often exposed, often rocky. And so it's kind of where these meet is where most of the missions in the past happen. So what I'd like to talk about is what happens if we kind of ignore this for now, because the one thing we found is that if we give engineers a goal, NASA engineers are amazing, and if we give them a goal, say this is what we want to do, they'll find a way to do it. So now that we know so much of Mars with all those data sets, can we just focus on the science, say this is what we want to do, and this is what we need to get done, and then let the engineers do it? And so that's what I'm going to be talking about with this talk. Let's say we just create a mission planning paradigm there, say that we have most of the data that we need for Mars to decide where to go, and then figure out what we need. And so that's what the rest of the talk here is, kind of picking out where I'd like to go and how we think can we do that. So if we're going down this process, this is a thought kind of exercise I had. What are the science questions we want to ask? And this goes back to the earliest days of Mars. We want to know, did life ever exist on Mars? This is kind of a main motivation factor for most of the missions. Big question I think still needs to be answered. And how do we actually do that? So then once we have the question, we pick a place to go and test it. And we found, early on in Viking, we found that we can't just land anywhere and find it. If in order to answer this question, we're probably going to have to try many different landing sites, many different ideas, places to look in order to ferret out this information. If the information is there on Mars, it's going to be a difficult thing to find, and we just have to keep working at it and try different spots. And one of the great things we found is everywhere we go on Mars, we always learn something new. That it's always so much more diverse on the surface than it is from orbit, and pretty much everywhere we go, we can learn something new. So I'm going to talk about a relic hot spring site in Patera. I'll be talking much more about that in a moment. And for now, we'll just say that's a place I decide to go. What does it take? So now we need our objectives. We want to be able to look at centers for preserved biosignatures, figure out what the environmental conditions of this is. So these are the motivating scientific questions. From here, we can figure out what data sets we need, what kind of sensitivities. What does it take to actually have these mission objectives be possible in order to answer these questions? And then, at that point, we have all of the constraints we need to give the engineers. Do we have instrumentations that can do this now? Do we have to invent new instruments? Do we have to wait? Is it even worthwhile to go to the site to answer these things? That's always a question I worried with past missions. We have these goals, we want to send the rover, but maybe we're not quite ready. Maybe we don't know where to go. And especially with the Mars sample return, we're going to spend maybe $5 to $7 billion on 3 missions to go pick up samples to some place. And maybe we don't know enough about the diversity of Mars at this point to go and select a spot. NASA's selecting a spot anyways, but that's a question that I think some people in the community may have about whether or not we're ready for that yet. And so this is a process that will then ask, what do we need to be ready to do these questions? So getting back to the motivation and kind of the methodology of how we want to find life on Mars. I'm a geologist, I'm not a biologist, so this is kind of my take of listening to lots of biologists and astrobiology people in these meetings talking about what it takes to look for life. From what I can tell, there's 4 main things we look for when we're trying to pick a place on Mars. We want a place where life can develop, a place with water, energy, protection from UV radiations, and enough chemical resources for life to happen. Next, we need a thing to concentrate. If there's a few cells there, they may be happily living, but chances are we're not going to find a few cells doing their thing in all of Mars. We need a place to kind of focus life in order a way to preserve it, and a way where we can go find it. And then a method of preservation. If life lived 4 billion years ago, that doesn't help me now. It needs a way for a sign for us to go and find today. We also need landform detectability. Like there may be a spot on Mars that might be teeming with evidence of life fossils, but unless we can use orbital assets to kind of find it, it's going to be hard to see. And all of these things kind of lead to kind of 3 main places I found. There may be a few others, or there's definitely more than these, but a lot of the areas that have been suggested again and again for landing sites kind of fall into these main categories, like deep crustal, hydrothermal, places that were warm and wet, deep in ancient Mars, deep in the crust, that could have been nice places for life, just like life all throughout the interior of our Earth, that have now been exposed, and we can see that kind of environments. Sedimentary lakes and deltas. This is why we kind of went to Gustav Crater for the Spirit rover, as well as to Gale Crater for MSL. These are great places where on lakes, and lakes are great places for life to form. The sedimentary layers are perfect for concentrating as well as preserving biology. And plus, they're incredibly easy to see from orbit. Sea and deltas, sea and lakes are very easy to map, so we can actually find them well. And also volcanic hydrothermal. Now, for a number of reasons, these are the ones I'm going to focus on in this talk. But I also think that this is typically much smaller scale than the areas we see here, but also quite interesting. And especially in my talk title, I talked about pinpointing. And new observational data sets, I think, really allow us to pinpoint on a few of these volcanic hydrothermal systems that have a lot of potential. So going from the volcanic hydrothermal, the main product that we see on Earth in those environments are silica. Silica centers, SiOH typically. And so far on Mars, we've positively found with morphology and with composition 2 places that have seen this. We have this home plate observation, which the Spirit rover in Gustav Crater happened to kind of come across. We were looking for a lake. We went there looking for a lake, and we find a volcano deposit, which is part of the amazing story of Spirit, but one of the cool things we found. As well as this Nilipatera deposits, these little white deposits in there in Nilipatera. And I'm going to be focusing mostly on Nilipatera for a number of reasons. I think that's a very important place to go. And but the same kind of methodology to kind of create the mission, create the instruments, create the data sets to go here could be also used in this kind of site as well, or if we find future discoveries of this. And so one of the things I like to point out here is we found this by accident. We went there looking for a lake, and we didn't expect to find this, and we came across an incredibly interesting astrobiological site just kind of wandering around. And that's because we were in old Nowakian Mars. And there's only a very few places that we're able to actually drive around so far in Nowakian Mars because it's so rough, because it's so kind of hard to get to. We've kind of avoided that with a lot of missions. And if we just happen to come across these sites where we happen to go there, it kind of tells me that there's probably a lot more of these all throughout Mars that we just haven't found yet. And that future exploration will find incredibly diverse and interesting sites in the years to come. So focusing on Nilipatera, I'm going to talk about the caldera. So this is a volcanic caldera. Nilipatera is the name of the entire caldera, and we're going to focus on this little cone here, Nilitholis. It's next to this kind of bit of evolved lavas. They've been very interesting, chemically evolved, more like dacite, a bit more silica-rich than we typically see on Mars. You often hear Mars as a basaltic planet, and a lot of the volcanics are, but in this place here, we do have probably some of the greatest volcanic diversity that we have on Mars. So focusing on this cone here, this is Neely Solis, we found these little white deposits here. By looking at hyperspectral data, we were able to record kind of what these look like in a number of different colors through the near infrared and ratio them to the background to kind of highlight the spectral properties. One of the main things we found in each of these white specks here is this 2.21 absorption feature, which is most identified as SiOH, hydrated silica. And wherever we look in these, we see this incredibly strong signature, indicating that this material is, again, compositionally confirmed as a silica, possibly Silica Center kind of idea. The center term can be a little confusing. It's more of a morphology than necessarily a composition, but it's often used interchangeably in some contexts, and I'll probably end up using it interchangeably here because we don't really have good morphology because all we have is satellite data here right now. So again, this is an oblique view of the Neely Solis and all these white deposits, and it's not just a couple, right? We see this, every place here we see this white spot is a place where I was able to map out the spectral signature from these kind of fan-shaped deposits, a mound here, a whole field, as well as a few places near the cone of this, the peak of this cone. And kind of zooming out, like I just talked about all these deposits here. These are, I will call the proximal deposits. We also see the same spectral signature here in these distal, as well as the edge deposits, and down here in the southwest. And so this isn't just a couple of features on the side of a volcano. It's an entire field of these kind of silica depositional minerals. And they all have this spectral signature, so we see, again, combination there. Like, they may have different processes that form them, but we all end up the same kind of material throughout. I want to focus on these ones in the southwest. These here, they're not over on the proximal, they're mostly surface deposits, like surface mounds and drapings. But here, they're all excavated by these kind of impacts. To me, that's incredibly important. This is a place where not only is these features kind of the last gasps of hydrothermal processes on this volcano, but they are actually interbedded with the volcanics. They are buried. So this most likely have been, whatever process is forming these has probably been going on for quite some time throughout the lifetime of this volcano. And I don't really like coincidences. I don't want to think that were just a few deposits buried here and these, like a few of the main craters that landed here happen to expose them. To me, the fact that they expose them means that there's probably much more that if we had more craters, it would see. But that's a difficult thing to go down and definitely difficult to prove. But chances are that this Silica Center is a fairly widespread phenomenon in this particular place. So I'm going to zoom in a bit more to show about just what the landforms of these create. This is looking at the side of Neely Solis. We again see this fan-shaped deposit. Almost looks like possibly a spring may have come out there and then deposited silica as it flow downhill, as well as this mound of silica material there, which we will then focus in. This is about 100 meters wide. Using topography, we're able to kind of do a cross-section and show it's about 20 meters high. So it's a fairly large mound. From this data, everything we see, all the pixels show this kind of Silica Center, but we don't have the ability to go and do a cross-section, do a coring, so we don't know if it's just like a surface cover or if the entire environment is this material. Luckily, these type of silicas and volcanoes are incredibly well studied. People have been interested in this for the biology of it for a long time. They've also been very important for mineral deposits. The hydrothermal things concentrate economic minerals as well as geothermal heat in a lot of places. So these kind of things have been well studied in the literature. And so we can kind of take that knowledge on Earth and kind of apply it to Mars based on what we're seeing. So here's a caldera setting kind of drawn from a terrestrial system. We have a cooling magma. It heats up the groundwater. You have silica saturation dissolution process going on to create supersaturated silicas in the water. They come to the surface. They deposit, create hot springs. And all those wonderful features. So again, what we have on Mars is we see these surface deposits, but again, that's only the veneer, right? So there's this entire subsurface process that produces this. And this is also, I think, one of the big advantages of this site. The fact that the volcanic nature of this means that everywhere from where the volcano magma chamber was up into the surface is a place that was mobilized by this water, potentially. And one of the difficult things about studying Mars is that it's very surface-driven, right? All of our orbiters can only look on the surface. All of our rovers can maybe move some sand around. We're hoping to send some drills, I think, in the next few missions to get a couple meters down. But we're really stuck to studying the surface. We have some radar that can do some ice deposits as well as some lava things in the few top 100 meters, but really we don't know what's going on in the subsurface of Mars. And a common idea using modeling is that we think there may be a deep buried hydrosphere, a place that even on Mars today, it's warm enough that you could have some water deep underground, which is completely blocked off from the surface by a cryosphere, where the surface is permafrost ice, but if you can get down a few kilometers, you can find a place that's still warm and wet enough. And this is also important for a possible biosphere. People sometimes talk about a deep buried biosphere, that if you ever had life on Mars, ever, most likely this organisms would work their way into the crust, work deep, and they could still be there today, following this buried hydrosphere, still living their thing, just cut off from us by several kilometers of very difficult to excavate dirt. And this is a place that, even if sinter deposits, hot springs, are often considered places that have all the things you need to create life, but the actual process for creating life is still a very big unknown. Just because you have the environment that's habitable doesn't mean life appears. And I think that's one of the big advantages here, that if life at this time ever existed anywhere on Mars, it most likely followed the kind of deeper hydrosphere as a place it could have survived. And this is a place where you could actually communicate, by connecting these channels through the deeper hydrosphere up into the surface, and may be able to kind of create a highway for anything that lived deep to kind of come up and be preserved in these surface deposits. And so yeah, so these, even though we're just looking on the surface, and any kind of mission that will go there will only be able to look at the surface, it might be kind of communicating this kind of deeper environmental, deeper community of Mars. Also going to the preservation. This is a chart from Farmer and David Emery, looking at how different materials preserve biosignatures, preserve fossils. And one of the least stable is ice. Really great for recent paleoclimate data, or spores and that kind of thing. But it's not great for lasting billions of years. It'll melt and climate change happens. And then all the way down here, one of the most stable, one of the best substances for actually preserving biosignatures is silica, which is exactly what we're seeing. So this is the type of material you want to look for finding evidence of life. Like if life was there, it's one of the best materials to find it. And so this is, for all those reasons, are why I think this area is a worthwhile place to check for habitability. So now the idea is, how do we actually go do that? Chances are I'm not going to be able to get NASA to send a $3 billion rover to go roving around there. Chances are we'll probably need a more focused mission, a bit more tailored for finding these questions. So what does it take? We kind of already talked about briefly what the mission goals are. We want to check these centers for life. Now, that's crazy, really easy to say, right? But incredibly hard to actually do. And this is the one where I think many people at SETI, many people throughout the community have been working on how do we actually tell if life was ever there? Does it need macrofossils? Do we need biological signatures? Like, what does life actually look like on Mars? If we see this, how do we know for sure there was life? So that's a question that I would love people to come with, talk with me later and say, oh, I have this instrument sitting around that could do that perfectly. That would be in the ideal, but I'd rather have maybe this is the thing you need to do to be able to try to constrain that answer. We also want to know what the hydrothermal environment, what were the temperatures, pHs, all the conditions of the fluids that form these deposits. If we do find life there, we may only find, yes, something was living. If we can constrain the hydrothermal environment it was living in, we might be able to find more about its evolutionary history, what kind of environments it likes. And I mentioned that this is one of the most diverse volcanic places on Mars. And so as long as we're going there, we should consider sending some instruments to understand this volcanic history. Why is it so different than everywhere else on Mars? Did that difference lead to these deposits? I've looked all the other calderas I found on Mars, and I've never seen anything similar to this. Could that be just because most of the other ones are covered in dust and they're there and we can't see them? Or is this fundamentally different? I have some ideas. I think that it is fundamentally different, but that's something we won't know until we start checking more on the ground. And then what kind of mission type, right? Do we need a $3 billion rover like Curiosity to go and drive around with instruments? Is that what it takes to answer these questions? Or could a cheaper lander mission just look around, maybe send a drone, pick up some centers, bring them back? Do we need a sample return? Maybe there's no way to send the instruments we need to Mars to answer these questions. Maybe we have to bring samples back. And before we start sending missions to go hear it all, it's good to know what it takes to actually answer these questions and what type of mission is required. And then we can figure out how to actually fund it, how to build it, and all those steps. What kind of instruments? And this is a chance we know what we want to look at. We know these centers we want to see. What are the instruments we need? Do we need imaging, compositional data, biological? What are the things we need to create a suite to make not only each instrument great, but make the whole combination of instruments better? So these are the kind of motivating questions that I want to look at. So one of the things that we want to do once we kind of exhausted our use of Mars data We figured everything we can using spectroscopic imaging and high resolution. We then go to places that we can see similar features and kind of get more in depth on Earth. And so that's when Mars analog selection comes in. And these features, luckily, we have Yellowstone, geysers, Iceland, more Yellowstone. These are common on Earth, and there's a few dozen places that I've kind of considered as good analogs. Places that had geysers, hot springs, fumaroles, all these different mechanisms have different water supplies, different kind of subtle things that lead to these center formations. We also want places that have both active and relic, so we can, relic is what we're going to see on Mars. That's all we're going to have there. But having a place that we can see the transition from active to relic will allow us to understand how does what was there when life could have been there lead to what we see there today. We also want some place that's kind of basaltic to match up Mars a bit better, as well as an easy and safe place to go get samples to work, all those fun things. And after a lot of work and selection I'm not going to talk about today, we decided that Iceland was the best suited analog for this. And I don't know if anyone's been to Iceland, but it's beautiful and so Mars-like and so volcanically active. There's a lot to work with. Here we see kind of a general tectonic map of Iceland. The geologic background is that it's a hotspot on top of a ridge, so you have a lot of overlapping volcanic processes going on. And we see that all these little red dots here are the high temperature hydrothermal fields. And so this is the project that I'm currently engaged on, to go there, try and find analogs in Nilipatera, figure out how we can test out the instruments, test out the mission selection to do what we need to do. So my past summer, last summer there, I went to pretty much most of these little red dots to try and figure out which ones have the sinter deposits that we need to study Mars. And I selected 3 of them, which I'll briefly go into how we're going to each use them to kind of build towards what a Mars mission will be like. And this is where I need to apologize that I'm going to try my best, but I can't speak Icelandic, and I'm going to butcher these names horribly. And if you know how to pronounce them, I really am sorry for what I'm going to do to your ears. So the first one I'm going to talk about, this is the HV actually sounds like a K for some reason. So it's like caldera. Sorry, again, I'm going to butcher. So I'll just call it caldera. So this is up in the Western Highlands. It's a place that has both active and relic centers, often very close in relationship. So this is probably as close to what Mars was like 3 billion years ago as we're going to get. So we can see just what do the microbial communities look like there. Where do they live? How do they live in temperature-dependent ways according to the hot springs? And then start to see how we go from these active to the relic center process. What do we lose in the degradation? Then we're going to go to Grenadier down here in the far southwest. This is a bit more low activity site. There's high regional activity, like there's a lot of springs around, but the site we're focused on is a bit more cooled off. We no longer have active center formation, but we do have a lot of fumaroles and a lot of sulfur deposits. And so it shows that there is more than just center. There's a bit of an evolution of compositional history there, which was great for figuring out geologic history and environmental change, but can kind of complicate where life's going to be preserved and just what kind of environments at a given time is going to be there for life to hold on to. And then finally, we'll be looking at Lai Shoal, way out here in the west. This area is far off the current volcanic kind of centers of Iceland and is by far the most relic site. This is old. It has not really been actively building for quite some time, and it's probably most close to what we'd go see on Mars today, except Mars has been sitting there for 3 billion years rather than a couple thousand. So trying to take that and expand out. But if we can't do what we want to do here, we probably won't be able to do it on Mars. So we'll start with Grenadier. We see here the active steam vents going on with many active pools, showing some of the diversity of features on top of each other. We also can map out active microbial growth zones, and well as the environmental conditions that they are. We can understand temperature and pHs here. In one sense, that these are 2 pictures taken about 10 meters apart, right? We have an active vent currently spraying out 24 hours a day. We see actively growing centers being deposited, even some sulfur. You can see some yellow there, a variety of compositions happening there, whereas this one has absolutely no activity at all. Historical records show if you come here 100 years ago, this was just as active as this, but for whatever reason, the geothermal plumbing has changed. It's shut this one off and has moved over somewhere else. And so this is kind of a complex story, right? So there's not only was life there, but there's a complex temporal change of this was active and then this was active. And if we're trying to find life in there, understanding that story is also key. And on Earth, that's what we do. We go to these places, we look at context, we look at superposition, we can kind of build this story. But the big question is, like, how do we do that on Mars? What do we need? Do we just land at one spot and then can look around and do that? Or do we need to drive up to each of these and like take samples, take cores of each? Is that how we're going to be able to break off the story if we actually go to Mars? And going and testing out all these different scenarios for the different missions is a key part of this process. So this is an aerial map I made of this site using an unmanned aerial vehicle. We can get some, kind of see there's a walkway, so it's a pretty good tour site. It's a pretty cool place to look around. We see a lot of these springs that then create the little center aprons. I'm going to focus in on 2 spots I think are pretty illustrative of what we're kind of looking at. One's up here first and then over here. In this site here, we have typically our springs are up to the top, and then they kind of flow downhill here. And just for the fun complexity of these kind of systems, where we see here is kind of the main channel coming down. And this kind of darker area is where there's very little life. Like that water is pretty much boiling, and very little is like growing there actively. It's usually flowing pretty fast. And then as we get away, we have the temperature changes. It cools down a bit, it slows down a bit, and we start to have different minerals precipitate. So we see more of a sulfur-rich, this kind of yellow apron come out. And with each one of these, you have different kind of microbial communities that kind of map to that. And so this is like, we take this to ancient Mars, and we see a ribbon of maybe something that's more habitable there, and trying to figure out how we can go and read from the rocks, the mineralogies that might exist on Mars today, to the temperatures that were there 3 billion years ago, what might help us to kind of build out that kind of habitable environments. Going here, this shows that cone I showed that's extinct, right next to a couple of these pools that are very active. And it shows the fact that things change quickly, right? This was once 100 years ago very active, and since then the plants have kind of come around and taken over, whereas these ones are still growing, still kind of keeping the plants at bay. And this shows that even when these are active, you had a complicated history of changing environments. Like at one time, this was probably a very habitable place, lots of energy, lots of water, but now not so much. Whereas here has the kind of more energy-intensive resources for things to grow. And so kind of knowing that this kind of changes happens very quickly, even while some are still active, and then eventually all this shuts off, and then it all just ages, is kind of a key question to answer. We're moving to our next site in Greta Beer. This is the mound I was talking about. Has another walkway, because a lot of these are fairly big tourist sites. So there's a lot of springs in there. You see this massive vent that's always shooting out just across the way, and one of the larger power plants, geothermal power plants in Iceland in the background. But this area, there's no real center formation now, no springs coming up right now. But you see a lot of places where you see old centers forming, or old centers that have formed there that are now kind of stopped. And on top of that, you get all this yellow. This is a sulfur deposit. And so if you go and actually put your hand on the ground, it's very warm to the touch. Like you still have fumarole deposits. And so for whatever reason, the water has kind of shifted away. It's most likely due to the fact that this company started drilling and taking away all of our water. But again, the water has shifted away from here, and we've gone from a very water-rich, silica, possibly more habitable environment to this kind of less water-rich, fumarole, acidic, sulfur-rich environment, which for different life may like that, but it's important to kind of be able to read that difference in the rocks. As well as trying to understand, the morphology here. So here's kind of an example of that. So here's, this is a picture from Grenadier just off the boardwalk, where we can kind of see this old pool that probably formed here. We can see finely laminated centers around the edge with a circular fashion, which is then filled up. Here's possibly maybe like earlier in the history of this, it looked maybe like that in Grenadier. We see still active, still forming these kind of circular features. And then maybe when this gets older, it then evolves, or that eventually will evolve into something like this. And then as it loses water, we'll transition to a more of a acid, sulfur-rich environment. And so again, what are the studies, what are the measurements, what are the data we need to have to be able to reconstruct this? And how do we put those onto a rover or some sort of mission to Mars? Another part is, back to the exploration aspect of it. So this is kind of, it's maybe hard to see here, but this is the kind of dome. This is looking in the opposite way from the boardwalk. So you see the boardwalk coming over. I tried to project this in the computer. But this is a mound, just like we see the mound in Neoptera. They're both about 100 meters wide, so we both have like a similar kind of spatial idea to look at, whereas this one is about half as tall. So if I was trying to reconstruct this, I wouldn't want to just look at it from afar. If you look from down here, you're just going to see a mass of things. You miss all the details of the individual silica springs that once existed, that once could have been hotspots for microbial life. You miss a lot of the changes from sinters to sulfates. And so it kind of tells me that you kind of need to get in there. And so by understanding just what it takes to understand this, like, so as geologists on the ground, we can go out there, we can map it, we can figure out what happened, and then we can figure out what will it take, what's the minimum number of samples that we need to have to be able to understand that. And that will then inform us what we need to have at the very minimum to answer our questions when we go to Mars. So finally, I want to talk about Lai Shoal. This, again, is the most inactive place. So this is the oldest. There's very little activity going on here at all. So it's the most relic centers, very brecciated. I had all these great drone movies here, but PowerPoint really didn't like them. So I'm mostly going to show some slides to kind of get an idea of what this looks like. So we're kind of spinning around this site. So it's several acres. This is by far our biggest site that we're working on. And all these little mounds here are just, they're old pools. You can see them kind of, the remnants of the, what the pool's like edges were. You can see these like drapings that used to be there. And this is just pool after pool after pool after pool that kind of created this large field. And so this is the closest thing of what I've seen on Iceland to what we're probably going to find on Mars. You know, there's many places on Earth where we have 3 billion-year-old sinters, but they typically get buried and altered and metamorphosed, and there's nothing like what we'd see on Mars today because, again, Mars has been so stable that we can see incredibly old deposits on the surface. But here's a place where we can see somewhat old deposits on Earth. And so finally, this is a close-up as we're kind of flying over. All those nice pools we saw at the previous sites, they're gone. All the nice little terracets, the little places where you have little pools of water as it's flowing down are gone. What we see is a jumble of rocks, you know. And this most likely is what we're going to be doing with Mars. Now, if you're walking around, like really kind of looking at rock to rock, you can really start to tell the difference. You can tell where the springs were starting, where the kind of terracets kind of happen in some places, kind of reading these rocks. And so understanding, being able to go here and figure out just what we need to do to reconstruct the site, to look for habitability within these rocks, is going to be the critical part of what we need to do before we go to Mars. So yeah, as I was saying, once we know, like, we can go on the ground, we're going to send geologists next summer back there to map out what is the geologic history, what is all that, and then try and figure out just how many samples we need to approximate that. And that will inform all the decisions for designing a mission to Mars. And now here's a rock we found there. This shows where it kind of is a distal deposit of the center that hit some grasslands, which kind of fossilized the grass. Like, that is the smoking gun of life at these sites. When we find this, we know that it interacted with life. And I would love that on Mars. I would love a place when these centers on Mars show that they hit some grasslands and develop that. But it's probably going to be a lot more subtle than that. And that's going to be the key question of this, is how do we go from the centers to say that this centers had whatever life was like on Mars? And again, I'm hoping that some people at SETI have been racking their brains on that for years and years and years and can help me figure out what instruments we need to have, what's the next grant going to be that we have to write to push down that question to get someplace that we can make this mission worth happening. And so with that, you know, all there is to let's go explore. Thank you. Any questions?
All right, great stuff, JR. Thank you very much. Do we have questions?
Thank you. Great talk. Since we're talking science-focused and not engineering-focused, what could you do with people on Mars that you can't do with robots?
Could do with people on Mars. The biggest thing there is that you can just have another magnitude of samples. So what would take a rover, you know, a month to do, you can do in a day with a person or less. And where, you know, we're going to spend 3 missions and probably $5 to $7 billion to bring back the Mars 2020 sample return. That's going to be 100 grams of material. And, you know, $5 billion to bring 100 grams of material here. So that's huge. Whereas if you had already invested people, bringing 100 kilograms of rocks and samples back is kind of trivial baggage almost with like how much material is going there and for. So it's really a magnitude of how fast you want to do this and how many samples you can analyze. And again, if you're going to bring everything you need for a laboratory to get people to survive, throwing in a few of the latest instruments as part of our lab to keep them busy while you're there is a trivial thing. So just that kind of process. Again, once you can ignore, basically by bringing people there, you're ignoring the cost aspect of it, and that allows so much more science to be done. Yeah, so that's really the biggest, the magnitude of how many samples, how fast you can go through each of these deposits. You know, like a rover, like again, these are a few kilometers between that mound, that fan, and all that. So like, you know, if you had a 10-year-long Spirit mission or opportunity, like that could eventually visit them all. But you do like the Apollo mission, they could have done that in a couple of days. And so that's really what you gain, is the ability to interact with so many sites, as well as kind of quickly understand what you have and then plan for the next day.
One of the more interesting places to look for possible origins of life on Earth is these hydrothermal vents at the bottom of the oceans. And it looks like the northern part of Mars might at one point have had something like an ocean. Is there any hint of anything maybe like a hydrothermal vent there that you've come across so far?
So when we're talking hydrothermal, we're especially looking for places where we have the morphology and the composition. Like that's when we say we have the smoking gun of this. And so far, again, only the 2 sites, and most of them were rather high or where we had that. The issue is when you get to the oceans, right, there's so much volcanic cover, there's so many sediments that they've just really blocked everything out. So unless you're going up there and you're coring through a few 100 meters to maybe more of materials, it's going to be really hard to find that. So again, we have people scouring all that, trying to find places where even craters have penetrated through that to bring up deeper materials. But then in the process, craters are very violent, right? So these kind of life are often signatures of life, signatures of these centers will be very hard to survive that kind of process. So like again, there's a good chance that that could be up there. Again, we have, if water was there, there's a lot of volcanic activity that could have been creating that, but it's just been covered by so much stuff that unless we send a lot of missions, a lot of very specific kind of drilling processes, it's going to be hard to access.
So I kind of have 2 questions. They're related. On the one hand, if we send a rocket, a lander to Mars, how do we ensure that the microbes that we have on our planet, whether they're virus, bacteria, whatever, doesn't get there and perhaps live? I mean, it sounds like nothing's living, but will it die when it gets there if we send some? Or if so, could it mix with what's there and create something that we think was there that never was there? So that's the one direction.
Yeah.
And then, of course, if we bring stuff back, probably more dangerous, because if there's some proto or living thing, how do we prevent it from getting out here?
Yeah, so that's a critical question for a number of places, especially you probably saw over the summer they found the water on active Mars today, and places there where we think that life could possibly be active. Like that's a huge concern for exploring that. These are, whatever we find here is almost certainly going to be fossilized, trapped. So I think that's, the chances are that we'll bring stuff, and all missions that go to Mars, everything leads is always well sterilized, well characterized, as good as our ability to do it is. And so chances are that we'll have a false detection is probably pretty minimal, because we'll be looking at something very different, and we'll be doing our best to characterize what we do have. You look a little confused on that. I don't know if that's...
Yeah, I was just wondering, like, as the rocket goes through the atmosphere,
Yeah.
You can do all the sterilization you want down here on the ground, and then you send this thing through the atmosphere, and it picks something up, takes it along.
Well, again,
puts it
usually the way that
down
they kind of
there.
work as shells, right? So usually whatever is touching the atmosphere is kept on Earth, and then it's usually the payload that's been well sterilized actually is what lands on Mars. So there's a number of engineering protections until you actually get to Mars.
Okay.
So again, like if this was a place with active water, then I think that's a much more worry that whatever life we have would get into there and then have everything it needs to survive. Because we're still on the surface of Mars, we have high radiation, so it's hard to think of how any life we have here would be very happy at this particular site. It would quickly either die from radiation or just not be, it might survive, but it probably won't actually grow for here.
Even something that was in a larval state. I mean,
Yeah,
there
like,
are
again, like a lot
things
of those
that
things-
live here. They seem to just wait for years, and,
So again,
and like
it
in
could be
Death Valley, they
It could be
all of a
fine
sudden-
sitting there for 1,000 years in this little larval state, but it probably won't get at least at this site, it won't get the water and the environment it needs to actually start growing.
Okay, thank you.
Yeah, I was thinking you early showed Lovell's canals.
Mhm.
And to be gentle, he certainly overinterpreted his data and, told a good story and got people really hooked on those dying civilizations. How are we guarding against doing that again?
Yeah, so that's a common issue I have here. Like this site, I kind of painted a really beautiful picture, I hope, of hot springs of life. But again, all we have is data from this satellite and a few spectral pixels to say that this is a composition. And then everything else is just putting kind of our Earth biases here. So the best way, like, I'm not sure, I don't know, I think being aware of that process, our ability to be optimistic is, I think, a way to do it. Also the fact that there is, every site that if I want to go here, there is the other guy who wants to go to a similar site that's not this, and he's going to keep me very honest about this site. I've seen that happen a lot for this site in particular, and that's the community working on that. And at some point, though, answering kind of these, curiosity of flagship missions, saying one flagship mission to Mars is never going to understand all of Mars. There's too much diversity, too much local scale things that are just very interesting to do. And so that's why sending a mission here, sending like dozens of missions to all of these incredibly interesting places is how we can kind of guard against putting too much value in one spot. And especially, I think, as commercial rockets make space travel more affordable. Like we just had, the Blue Origin kind of had the first reusable rocket. Like I think that getting to Mars, the cost boundary, the work effort to do that is going to be coming down in the next decades. And so now we don't have to worry about what's the perfect place for this mission. We can say, okay, these spots, these top 10 spots are all amazing. Let's just go throw a mission in each of them. We can tailor it using engineering and all the kind of methods I talked about to kind of keep it scalable and do these specific things in a number of places to kind of hedge against the big failure of over-interpreting any one spot.
Okay, any others? All right, let's thank JR again. Okay, we have, don't go away quite yet. All right, I would like to present JR with our SETI Talk mug as a token of our thanks for
Thank you.
giving such a great talk.
Great time here. Thank you.
So we're also going to break with tradition because these highly coveted mugs are usually reserved for our speakers. But we also wanted to give one to Leonard today again to thank him. So this is, an extraordinary gift in exchange for an extraordinary gift. Thank you so much, Leonard. And for any of you who'd like to join Leonard as a presenting sponsor for the series, we're always interested in more help and appreciate it. And of course, it continues to help us put on this colloquium series and do other programs in education and public outreach that are important to us and important to the community. So thank you again for your participation here. By the way, for the excellent question on what we largely term planetary protection, there's a woman sitting directly in front of you, our very own Margaret Race, who is an expert and the leading researcher at the SETI Institute on the subject of planetary protection. So if you have enough money, you can probably get some attention from Margaret for a few minutes. But again, great questions, great talk. John, thank you so much. And thanks again for joining us today.